All right, welcome guys. Thank you for attending today's lecture. I appreciate it. As you guys know, there wasn't a Geary lecture yesterday. It was Veterans Day, so he didn't have a lecture, but we're still going to have one. It's going to be the same topic that we had last week, which was permutations. So let me write that out. I'm not going to go over the code for permutations because that's exactly what we did last time. We looked at the recursive tree and we built it all out and we understood the backtracking and how we actually get these permutations. But what I will do is just give a brief overview of what a permutation is. Let's say you have a number called n, and that n is equal to, making something smaller, to 3. Would anyone want to give me a permutation if you already know?
1, 2, 3.
1, 2, 3, perfect. So let's see if we can find a pattern here to see if we can figure out ourselves before I give it to you guys. Do you know another permutation? It's okay if you don't.
1, 3, 2.
1, 3, 2, perfect. Do you know one? Yeah, don't worry about it. How about you over here?
3, 1, 2.
3, 1, 2, cool. Okay, now in the back.
Yeah, what about 2, 1, 3?
2, 1, 3, yeah, that's also correct. Okay, I'll call you guys later for another question, don't worry about it. Anyways, so these are accurate permutations. If you guys haven't noticed, the pattern is that we have n numbers, and the order that these numbers appear actually matters. That's why there's a difference between this first permutation and this second permutation. If order did not matter, all of these will equate to the same thing. But for permutation, it does matter, and that's very important. So I should have probably called on you guys because there is 2 more sequences here. Do you guys want to say it?
3, 2, 1.
3, 2, 1. Perfect. And no? Okay, all right. Don't worry about it. It's fine. Joseph, you want to go again?
Yeah, what about 2, 3, 1?
2, 3, 1, yeah. No need to fight, no need to fight. Let's try to settle down. It's a big crowd today, so. Is there another one here that we're missing? No, you said that pretty quickly and confidently. Why?
Because it's 3 factorial.
Perfect, that's exactly why. The number of permutations we have is equal to n factorial. So the number of, I know I'm blocking the camera, so give me 1 second. There we go. The number of permutations is equal to n factorial. If n is equal to 3, in this case, the number of permutations will be 3 times 2 times 1, which is equal to 6. And as you can see, we do have 6. Perfect. Now, oh, hey, Paulina. We just have more and more people joining.
Yeah. It's popping out.
Okay, so you were here last time, so I'll just go over it quickly. The number of permutations we can have is equal to n factorial. And permutations order does matter in the order that that number appears. So that's why this first one and second one are different from each other, because the 2 appears first, and then this one, the 3 appears first. All right, so that was just a little recap. Any questions on this? No? Okay.
So the order you generate permutations matters?
Yeah, exactly. So the order that the numbers appear, not the order that you generate the sequence. So like we could have generated this one first, and then this one. That's perfectly fine. But what I mean is like these numbers themselves. And the reason I say that is because, and I'm not going to go over this, but there's something else called combinations. Where if n is equal to 3, just write it out. These two are the same thing for combinations. Because in combinations, the order does not matter. So these two is basically, hey, they have the same numbers. They have 1, 2, and 3. So it's the same thing as this one, because those also have the same number. But for permutation, this one is saying, hey, first comes 1, then 2, and then 3. But in this case, 1 comes first, but then 2, but then 3, and finally 2. So in that case, those two are different. Cool.
Just to clarify, there's only one combination and any number of digits.
Yeah.
Well, it's because of how the problem is presented, right? The digits.
Yeah, it's because we're given this n. So unless we want to do like subsets, I believe, we can.
Oh yeah, I remember that.
Yeah, we have all of these.
Yeah, that's how you do it.
Yeah, we have like those. I think there's a couple more, I'm not sure. Should have probably looked up the formulas for permutation and combination. I think. I actually don't know. Let me search it up. N factorial, n minus, oh, it's exactly that, cool. And then combination. Combination is a little bit different. They have this as R, so I guess I'll change it to R as well. N factorial, n minus R factorial, then times R. So yeah, that's the formulas for permutation and combination. I don't know. Yes, you guys want to know.
What does that give you? Like,
Um,
So that's the number of permutations or the amount that you select to put on the, like let's say you have 3 numbers, but you only choose to output 2 at a time, right? Okay, can you show them?
yeah.
Like make R
Okay.
or N to
So the important things to look at is the N and the R.
Oh, I see.
N is how many things you have. I don't like the word things. Give me a sec.
the element.
How many numbers? How many elements you have? Sure.
Total elements.
Yeah. N is the total elements, and then R is how many of those elements you want to choose.
Yeah.
So remember, we had 3 in the beginning.
Wait, look,
And-
can I see an example?
Yeah.
So a great example.
You want to say on the mic?
Yeah, you don't know.
You want to come up here? You don't want to be on camera?
Oh my god. All right, so a great example of this would be if you have 10 players. If you have 10 players or 10 participants in a race or something like that, and then you only want to choose first, second, and third place. So the order matters in which you choose, the first, second, and third place. So then in that scenario, it would be n is equal to 10, and then r is equal to 3. So you can then, I guess, derive how many ways you can choose of the 10. You can choose 3 different first, second, and third place winners. So it would be 900 times 8, which is 7,200, I think. So yeah, that would be for that. Or 90 times 8, 720, my bad. Whoa. 720 ways.
I don't know. There are
Come up here.
15. Okay.
Oh, I mean, but yeah, that's a.
Okay. After me. Oh, you know, okay. Yeah, she wants to go.
But
Oh wait, okay, sorry.
but yeah, but that's a I think that's a good example for permutations at the least. Yeah.
Okay. Say you've got 15 members in your NBA team, Miami Heat, but you can only have 5 players on the court at a time. That's how it is. Who's getting benched? Who's playing? That's a permutation. Yeah. Like that. Yeah, 5 at a time on the court. Okay, yeah, still there. And so,
10 times 9, 10 days.
what's the game?
Who's playing though? Like the Pelicans?
I don't know.
The sport or whatever.
It's basketball.
No, it's basketball. It's basketball. I mean, I could have picked anything else, but I thought
Because I
small
guess
numbers.
For some games, order doesn't matter, right?
Well, I mean, you want to get the best, team, right,
Actually,
playing on the
yeah,
court
she's
at a
right.
time.
This is combination.
What?
What you're talking about is combination. Because the order doesn't matter.
Okay, no, okay. Supposing that we wanted to have KD here and I don't know who else. You want the order in line, because maybe you want them to do specific things, right?
Yeah, that's not what you said though.
Okay, here.
She got you.
She wins.
What do you mean? No, you gave us a perfect example for combination.
Well, she wins in calling me out on the nonsense of how they're lined up.
Thank you, Paulina. You want to come up now? Get them back. Okay. Permutation, combination, the number of permutation sequences you could have for any number n is n factorial. Combination, order doesn't matter. I know Gary already went over this in the class, so I'm going pretty fast. And then these are just the formulas, and we're going over some examples. So, let's actually try to solve a problem now. Let's solve the traveling salesman problem with permutations. Traveling salesperson. Okay. The TSP. You're totally right. I'm sorry about that. Has to be gender equal, I guess. So do we all know what this problem is? Do we?
It's a refresher.
Okay. Does anyone know it? You want to say it?
I think I remember what it is.
Okay.
You need to take a tour and physically
Yeah.
square things 167
Yes.
when you start equation, because that's where you need to end the journey.
Yeah. So you want to do a tour? Should we or should we not? Let's exclude the weights. I guess we can make it a little bit easier.
Can you have another node in the middle?
In the middle? Where? Like here?
Yeah,
Because what?
you can scoop around, right? Like there's no point.
Oh yeah. Well, it gets different if I do stuff like that though.
Yeah, that's better.
Okay, so it is a tour. He's absolutely correct. A tour is you're starting at one node and you want to visit every other node and then finish at that one. But with the traveling salesman is that you want to visit every single node once and only once. So at most once. Okay, so yeah, a possible solution for this, for example, would be 1, 2, 3, 5, 6, 7, 8, and then back to 1. That makes sense because 3, 5, 6, 7, 8, and 1. Of course, you're going to start, you're going to start and finish at the same place. So if you take everything in between that, it's a set. It's unique numbers. There's no repeated. So how can we figure this out with permutations? Demba, did he go over this in your class?
I think so.
Fuck. Okay, I won't ask you then. Yeah, try not to say it then. So how can we do this with permutations? What have you guys noticed so far? If you haven't noticed anything, it's perfectly fine. I haven't really given out that too much. Okay, cool. So let's, just for now, to make it a little bit easier, let's remove the last one. Now we have 1, 2, 3, 5, 6, 7, 8. Another traveling salesman tour could be 1, 8, 7, 6, 5, 3, 2, and then 1. But like I said, we're dropping the 1. So how many numbers are here? There's 7 numbers. Let's keep it at 8. Let's say, let's just do that. Right? That part makes sense so far? Can I say that this is a traveling salesman tour? No? Why, Paulina?
Because from 5, you can go to 7.
Wait, what? Wait, sorry. 1, 2, 3. Okay, yeah. Sorry. No, you're totally right. I just didn't. I wrote this out without looking at it, so it took me a while. Yeah, exactly. From 5, you can go to 7. But these two we could do, right? So what are we generating here, and what are we verifying?
Possible route. Possible routes.
And you agree we can do that with permutations, right?
Yeah.
So we know that there's 7 nodes. You know what? I'm bringing this down back to 7. So we know that there's 7 nodes. Let's go ahead and create every single permutation for n is equal to 7. But there's something that we want to check before we actually add the next number in this permutation sequence. 1, 2, 3, 4, 5, 6, 7. So I had 1, I think I had 2, and then 5. That, you would agree, is not valid, right? Like Paulina called out. And what was the reason that you said it wasn't valid?
Because from 5, you can't go to 7. Like, I guess
Yeah.
it's not in the list.
Yeah, exactly. So yeah, you pretty much already have the right answer. From 5, there is no edge to 7. So every time we're running our permutation code, before we actually add that number in this index, we want to do another if. I don't know if you guys remember, but one of the first if is to check if this number has already been taken. If it has not been taken, then we know we can use it. The second if is if there's an edge going from 5 to 7. So in a for loop, let's say in a for loop we're currently at some number, we're currently at 7, right? We check, well, have we used 7 before? We haven't, so that's good. And now let's check if there's an edge from 5 to 7.
What do you mean if we have used it before?
Yeah, so like if it's already part of our sequence. Remember how in our code there was an if?
So that means that it could be repetitions, like in the...
Like if it's equal to 0, aka we haven't used it, then let's consider it. But if we have used it, then we do not want to try it again, because it's already in the sequence. So in our code, should have probably written it out, to be honest. But in our code, we had this if statement, checking if this number has been used before. 7 has not been used before. So now the second if that we want to try is if there's an edge going from 5 to 7. Here we know that there isn't, so we would never consider that. One that we would consider is 6. Then from 6 we can go to 7, and 8, then 3. But of course that is not at all a traveling salesman. You guys know why?
We're not finishing back where we started.
Yeah. So remember, we always have to finish at where we started. We started at 1. So once we have this sequence, before we print it out, we kind of want to do another check to see if from our last node, is there an edge from that last node to the first one? This case, there isn't. So we know that this is invalid. Are you going to ask me something?
No.
Okay. And that's exactly how you do the traveling salesman with permutations. Obviously, not at all efficient. This is still n factorial. So this is still an NP hard. So we can't do this in polynomial time. So it's not like we solved the hardest problem in computer science. It's just one way of doing this. Geary told us there's a much better way of doing it using this cutoff line. David, what was the name of it? Oh, you remember? Yeah, you were there.
There's like pipes or like segments where we can cut off.
Yeah, but what was the word he used? No, not the pruning part. Yeah, we do prune, but not the part.
They're like, you create like, kind of like a pipe, like a circle pipe.
Yeah, but what's the name of that? Like that segment that we cut off.
It is called, I don't know, I think there was something about it being like a pipe, but.
Damn it. Okay, so I just go over it. I forgot the name. Sorry.
Is that like a different algorithm, or is it like a
Yeah.
printing technique?
So
It's like both.
Yeah, but it can also be its own algorithm.
Yeah, it is, because you have to find those nodes.
Yeah.
Wait, is it when you find like the nodes that like if you take that path, you wouldn't possibly reach that thing and then cut off that path?
Yeah, exactly.
Yeah.
So you want to find the nodes that if you were to remove that node or that sequence of nodes, if there's 2 components, it's invalid. So what does that mean?
Is it like strongly connected components?
I think that's the algorithm. No, because we're removing nodes.
That's a completely different algorithm.
Yeah, that's Tarjan's algorithm. But we could use that one, I think. No, actually, I don't know if we can.
Beyond me.
Anyways, okay. So if we were to, cool. So you see this 8 and the 3 and the 5, correct? Let's say we went down the route of doing Can this lead to a traveling salesman tour? No, perfect, yeah. The reason it can't is because if we were to take these nodes and remove them, we now have 2 components. We now have, basically think of it 2 subgraphs. We have 2 by itself, and then 6 and 7 together, but separated from 2. So if we go down that path, we can either go to the 2 or to the 6 and 7, not both. So the algorithm, the optimization algorithm, is to find those nodes early on, that if you were to go down that route, to find those sequence of nodes that will result into something like that. Once you know those sequence of nodes, never go down that route. Never take them. because you know they would not lead to a solution.
It's just a pair of nodes, or is it?
It's a sequence. It could be multiple. It could be a whole bunch. Yeah, it could be a whole bunch. Cool. And if you're asking, can that, obviously, to figure out if this algorithm is even worth it, is we need to be able to do that optimization better than n factorial. Because n factorial is how long the permutation does. If that optimization is larger than this, there's no point, because that will lead to a worse time complexity. But it's lower than this.
I like that optimization would be like, would give us a worse time complexity, because like, let's say you have like a sequence of nodes, like a bunch of sequence of nodes, like every single time you're about to add an edge, like another node, you'll have to like run through all those things and validate if it's not a part of them.
Yeah, so to do that optimization, you need to use network flow.
Isn't that what isn't that it? What you were talking about? We were trying to figure out
What?
network flow.
When?
Well, you just said network flow.
Mhm.
Isn't that what Yuri was trying to?
Yeah, this is what I'm saying right now is like the question I asked him, if we can do that optimization step lower than this time complexity. And he said we could, but we have to use network flow.
That is network flow one.
Okay. Wow. So you start off with a source and a sink. And your edges are weighted, so you can think of it as kind of as water running through these pipes. That might be why you remember pipes. You can think of it as water running through the pipes. And you want to see I think it's the fastest route or the most efficient route from sink to source, from source to sink. I don't know. He's going to go over it next semester, I think. But it's really hard. Like, it's way worse than DP, obviously. But this is like the hardest concept, I believe, according to Ricky. And Ricky's a genius. But yeah, it's something like this. All right, so now we just learned how to do traveling salesperson with permutations. Pretty straightforward if you know how to do permutations. Now the next thing I want to talk about is how to preserve the order. So that if we had n is equal to 3, there's more. There's 2 more, but I'm not gonna write it. I'll write it. Okay. Okay. So these are the sequence of permutations in order. What does in order mean? As you can see, we have 1, 2, 3, and then we flip these. So now we have 1, 3, 2. Then instead of the 1 here, we have the 2. And then we have 2, 1, 3. And we flip these, we have 2, 3, 1. So there is some order to it. The algorithm we went over last class did not give us this ordered permutation sequences. Instead, it gave us 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 1, 2. Yeah.
Can you use the previous algorithm and then just sort the whole thing?
Probably. Yeah, that would work. Yeah, no, that would for sure work. But can we do it in a better way instead of n log n? Even though that's less than n factorial, it wouldn't really matter. Let's just pretend you didn't say that. So now the thing that you want to keep track of is while you're running this permutation algorithm, is you want to keep track of the numbers you've added already. So you'll be using a set. And in the set is going to be, I really should have written out the code for this crap. Oh, you know what? I do have the code. All right, give me 1 sec. Perfect, cool. It's so hot in here. Really? You don't think it's hot? Okay, cool. Submissions. All right, let's actually write it out. Screw it. Okay, so let's call this method called solve. You're going to want current one on and this added set. You want to print the sequence, if that's the case. All right. Then if cur not added, crap. You. All right, let's just cut it off there. So you want, like I said, you want to keep track of it in a set. So if I were to call this from my main function, go to 0, right? Yep, and then 0 and an empty set. Then you want to increment your u. So this is going over where we went in last class and what Gary showed us. And if the length of your set is equal to n, then you know you already have added all your numbers to the sequence, and you can just print. That wouldn't even matter because this wouldn't even run, but whatever. Else, you want to go over this range from 0 to n, where n is, for example, 3. Your current is going to be I plus 1, because this range starts at 0. Make it a little bit easier. There we go. If your current is not in your added set, then we know we can add this, at position U, we can add current and add current to our set. So that was really confusing. So let's run through an example. Let's say n is equal to 3. Initially, U is 0. So now U is going to be 1. This is not the case because the length of an empty set is 0. And 0 does not equal 3. So we can skip this part. Now we get here. So first, we're going to start off with 1. Current is going to be equal to 1. And it's not in our set. So in our position 1, which is right here, set that equal to current. So that's going to call, it's going to be 1 here. And I think I forgot my recursive. I did. There we go. So now we've seen 1, and we add it to our set. So now let's recursively call this. Now I'm here. So remember it was 0. This is supposed to be self. Oh, this is getting so confusing. Let's do something else. You know what? No, let's just leave it there. We can erase that part. I didn't use it. All right, cool. So nothing really changes, to be honest with you. At 0, set it equal to cur, which is 1. And now we can recursively call it. Now U is going to be 1, and added is going to be a set, which has your 1 in it. So when we run over this, we know that we cannot use 1 because we've previously used it. Instead, we know we could use 2 and place in this location because 2 is not in your added set. So go ahead, add it, and then recursively call it. Where does the order come from this? How can I explain it? Cool. Okay. So you obviously know that once you complete this and you backtrack, you obviously know you're going to get 1, 3, 2 because you incremented from your 2 to your 3. And then from there, you're going to reach that 2 that you missed, and it will be added right after the 3. And from there, that's how it builds the order. I know it's pretty hard to see, but it keeps track of the ones you have already added, and from the ones you are missing, those missing numbers, they will be in the remaining open spaces. So for example, if I have 1 and 3, my missing number is 2, but we know for sure that they'll be in front everything else that's missing, which is only this position. And whatever you put there, it will be ordered. Yeah?
So what do you remove from this step when you backtrack?
Yeah, I actually also missed that part. Because I have an if and an else. Should I? Yeah, screw it. I'm not going to do the if and the else. And then at the end, yeah, that's it. So that's all you really need for this. Because of course, once you try the 2, you get 1, 2, and 3. When you backtrack, you do want to remove the 2. And you want to add the 3. Therefore, when you recursively call it, you could use the 2 here in this position. So it's running through all of these. I don't know. Okay, let me know if you guys can see it, but you start off with 1, and then everything else is incrementing. So you get 1, 2, and 3. And then you backtrack and you increment the last one. And then the remaining is the one that was missing. You know you don't have the 2 because you only have the 1 and 3, so the 2 is going to go there. Then you can fully backtrack. You cannot add the 3 because the 3 was already added. And then you're finished with this 3 here because you're finished with the range. Now the one you can increment in this is this 1. So you can kind of look at it and you can see that there is some sort of order with how the first digit appears, then the second, the first pair, then the second pair, and the third pair. So that's why you want your 1, 1, 2, 2, and then 3, 3. So it's the same thing with these other ones. It's 3, 3, 1, 1, and then 2, 2. So like here you have your 1 and then 2. Then you still have your 1 and then 3. But here you used your 2. So the next one will be 1 and 3. So in a sense, like this column right here is also ordered. Because you know you can't use your 1. So the next one you can use your 2 and your 3. Then here you use your 2 previously. So this is ordered because you go from your 1 to your 3. And then here you use your 3 previously. So you can still use your 1 and your 2. So in a sense, if you look at it, like the columns are ordered as well. Yeah.
So, like, how is this going to help us with the traveling stuff first of all? Like,
Yeah, so this is completely different problem. There's a LeetCode problem. That's a hard cod.
I thought we were doing the traveling stuff.
Oh no, we finished that. It was that easy. It was like that straightforward.
Just doing permutations?
Yeah, we're just going over permutations.
So that's n factorial. I thought we were optimizing.
Yeah.
There's no optimization.
No, there is an optimization for this part, and that's what Dave is going to go over. Yeah. So, no, for traveling salesman,
Oh, so this is just generating permutations?
yeah.
Oh, okay.
For traveling salesman, the worst case, it's still going to be n factorial. If you have a complete graph, there's no nodes you can remove in your optimization.
Yeah, that makes sense, yeah.
Okay. So this problem is called permutation sequence. Yeah.
So you don't run this like inside of a folder, right?
No, I just called it with
One.
with 0 and then set. Yeah. Yeah, that's all I did. Yeah. Okay, cool. Because you're taking care of it with this, and checking if it's in your set and stuff. So this problem is called permutation sequence. It's a hard on LeetCode, and you're given a number n. In this case, n was 3, and you're also given another integer called k, and you want to find the kth sequence.
That was going over this like towards the end.
Yeah.
To that problem.
Yeah.
Don't remember. Yeah.
Yeah.
So I'm gonna go one time.
Yeah, you're going to do it now. So that's why I went over keeping the order. Because if you can keep the order, then of course you can just index and see which one is that one. Doesn't work at all. Not one bit. You get time limit exceeded. Why?
How many test cases would you get through?
Oh, it doesn't tell me. Wait, actually, yeah, it does tell me, right? If I click on it. 123 out of 200. So this n factorial approach does a little bit more than half. But there's a better way of handling permutations for this specific problem. And it's very math heavy. Well, I don't know if it's math heavy. It's just math. But there's some sort of pattern where you don't have to do the n factorial algorithm. Instead, you have to do something else, and that's what Dave is going to go over. And he's going over it because he got it. He solved it.
Yeah.
All right, so yours.
Oh, I'm going over right now.
Yeah.
Oh, okay. I thought it was gonna
Are you guys math majors? No? You're all right? Minor?
minor.
No? Okay, I guess Daniela was able to get it because she's a math major. Is that, did you do what I did? No, no, this is something this was what we're going over right now.
Did you solve it yourself?
No, I never used the code.
Wait, can you push that code and then like
Yeah, I'll fix it, yeah.
Oh my god. I'm trying to put it on without breaking it. Okay, awesome. So you're given n. N equals, say, I'm gonna choose 4. All right, and then your k will be the kth. I'm gonna pick. So a number between. It's 1 indexed. It doesn't matter too much. So between 1 and 24, I'm gonna pick 19. Okay? So the way that the permutations are lined up is in a certain order. The order does matter. So the first one is always gonna be, in ascending order, and then the last one will be in descending order completely. Well, actually, you wanna do all of them? We have to do all of them. And it's gonna be 24 of them. So it's 1, 2, 3, 4.
Wait, we don't have that much time. I just want to let you know.
Yeah, but I kind of have to get the pattern.
Okay.
Okay, I won't give you the code. I won't give you the.
Then do n is equal to 3.
Huh?
Then do n is equal to 3.
Okay.
Lower the k and that's 4.
Hmm?
So 19.
I think that's 24 is the n.
Oh, so it has to be 19.
He wasn't doing 19 factorial. He
No,
was
no,
doing
no, no.
4 factorial.
4 factorial is. Yeah, 4 factorial is 24. So between 1 and 24.
Dude, imagine doing 19 factorial.
No. I think the actual problem caps at n equals 10.
Really?
Yeah, I
Just
think
solve it,
that's.
and my solution would have worked.
Yes. Well, I
Is it
mean,
really that? N factorial, 10 factorial? That could be that.
yes. But the thing
Yeah,
is,
capped at 9. Wow.
do 4. Okay. K has to be 1 to 6 in this case. So 1, 2, 3, 1, 3, 2, 2, 1, 3, like before. 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. And this is the 1th, this is the 2nd, this is the 3rd, 4th, 5th, 6th. Okay? All right? Okay. So they ask you for, so you want to generate the string of 2, 3, 1. All right? Where do we start? Any ideas? Any ideas? Do you see a pattern? Okay.
So it's like, probably we can filter by the first digit.
Okay.
So we have
So you want to get the
1,
first digit?
2, 3, 3.
Okay. So, well, I guess before we go on, do we have to generate all of them? No, we don't. We don't have to, because that would take n factorial. And you could solve this in linear time. So,
All of n?
yeah,
Wow.
yeah. Just like that.
Oh. Okay.
Yeah. All right. Okay, so we need external data structures to do this work. So what do we need? Any ideas? If you have n and k in numbers, they give those to you. What else do you need? An array of what?
integers where you can store like the different numbers that you're gonna generate for each index.
So you 1, 2, 3?
Yeah.
Okay, actually you do. But more specifically, what would be more useful than a list, an array?
One is string.
Set and less,
And why?
so you don't like repeat the values.
Exactly. So you don't have to repeat it when you're writing it down. That's correct. So you need a set. And the set is going to be all the numbers that will make up the permutation. So 1, 2, 3, and this is 0 indexed. And you'll see why that matters soon. Okay, maybe we do have time to write the code. We have the set, right? Now, what do we do, right? What else do we need to keep track of? Okay, so before we do that, let's actually analyze something. So the fourth one starts with a 2. Okay? Now, at first, how many times does 2 appear? Oh, actually, how many times does each of the first digit appear? 2. What is 2?
And minus 1, but I don't know if that's always.
Minus 1? What do you mean? You mean 3 minus 1? Is that the relationship? Hmm.
I think I remember from the other class, that's n minus 1 factorial.
Yes. Yes. So this is all 6. This is 3 factorial. But the amount each appears is 2. That's 2 factorial. So this is n minus 1 factorial. All right? So we need to keep track of all the factorial values. So we need a list of all the factorials, which fact, right? And it's a good idea to add, factorial 0. 1, and then it's 2, 6. So you need this. This is important. Because then you're gonna iterate through the value of n. Okay? Okay, so you're gonna change the value of n, you're gonna decrement it by 1. Okay? So you're at 3, but then n minus 1 is 2. So you want this value, right? Okay. So which one is 2 in? In which range of all these?
Wait, can you
Slow down?
And yeah,
Okay.
repeat a little bit?
What do you want me to repeat?
That array, the fact array.
This is the factorial values. Okay, it comes from this. There's 6, right?
Yeah.
6 is 3 factorial. How many times does the first digit appear?
Twice.
Twice.
So yeah, so it's twice for all of them.
Yeah, 2. And what is 2?
3 factorial. I mean 2 factorial.
Yeah, exactly. So it's 3 minus 1 factorial. So let's say we're here, we have to get this value. We're gonna actually store the factorials to start off with, right? And how long does it take to calculate this factorial?
I mean, you could use, I guess, like recursion, dynamic programming or something like that.
You don't need, no, not at all.
Why is
Like-
it list 1126?
Oh no, you
Yeah. This,
multiply.
yeah. So I make the first one 1. I make,
Yeah, you multiply by the I minus 1.
yeah, exactly. So I just keep
But then you get 6.
6.
You multiply the indexes.
Uh,
You
yeah, I
multiply-
suppose you can, and yeah, multiply the indexes, yeah.
Yeah.
So this is index number 3. You multiply it by the previous value you got. And so say maybe it's 4, index 4 multiply by the previous 6, and you get 24.
Okay. Yeah.
And that's
I actually didn't think about that. I didn't think about that, but good eye. But this is just to say this is factorial 3. Now we want factorial 2, right? This is the value we want, and here's why. So where is this one, right? What's the actual number? It's 4, right? And 4 is here. So we want give me a minute here. Trying to retrace my steps, what I did.
I have your code if you want to look at it.
You do have my code.
Yeah.
No, hold on. I don't want to look at it. I want to refresh.
I have a question. Is
Yeah.
6 important?
What?
Like 3 factorial is 6, is it important?
You're kind of right. It's not. It's actually not. We're never going to use this. But it's just constant extra memory to have an extra value in the array. We don't use this. Good point. So n equals 3, right? So you get the current 1. So let's say it has to do with the set. I remember now. So it has to do with the set. What if we subtract this by 1, 2, actually I'm going to pick a different color. Just because. 0, 1, 2, 3, 4, 5. I remember now. Okay. So this one it was 4. K was 4, but now we subtract by 1 is 3. Okay. So I want to map this 2 to the value here. What do? I want to turn this 3 into a 1. Why? Why do I want to do that? Why do I want to do that? Any ideas of why I want to turn this 3 from this one into this 1 in the set?
Wait, hold on. Can you repeat your question again?
Because we're trying to get this one, right? And the index is 4, k is 4. But if you want it to 0 index, we subtract by 1 and we get 3, right? What is 3 divided by factorial of n minus 1, which is 2? He's completely lost. 1.
No, I get the answer for it 2 divided, but like I just don't get the logic behind the whole thing. Wait, just repeat it one more time.
Okay. So basically, if k is 4, it's this one. We want to print this, right? But we want to get the first digit.
Oh, so you're trying to get the first digit.
Digit, yeah, exactly. And we also want to get rid of it in the set so we don't add it again. Okay? So we get that it's 3.
Yeah.
When you integer divide by 2, and 2 is n minus 1 factorial, you get where it's indexed in the set.
So you get the index.
Yeah. And then I will get rid of it.
And then you'll append it somewhere to store the answer.
No. I get rid of it. I just,
Get rid of it.
yeah. And then they're all reindexed. Okay? So now it's just 2 values, 0, 1, and it's 1, 3. Because then after this, we're done, right? So we get that it is 1, right? Because this would be 0, this would be 1, this would be 2. And then now we're only dealing with 2 numbers, because once we figure out that it's 2, now there's only 2 different numbers to work with in permutation. So there's only 2 different combinations. So n changes to 2, right? Because now it's 2 factorial different permutations to work with. And on top of that, we have to change k. Any ideas why we have to change k?
Because we reduce the number.
Exactly. We're reducing the amount we need to work with. So now the indexing changes. So what will we have to turn k into? So it works the next time we iterate.
1, because we just have 2 different.
How do we get to that? How do we get to that?
For like any case.
Yeah. Well, actually, it wouldn't be 1. We're actually going to turn this back into 1 indexing. And this is how I did it. This is just, so yeah, this is going to be 1 and 2. Okay. So how do I turn this 4 into a 2?
I mean, I think I get the part where you, like how you reduce the k, but I think I'm lost again with that 1 and 2.
1 and 2.
N minus 1?
Be-
Factorial?
Exactly, because now it's n minus 1 factorial you work with. There's only 2 different combinations once you figure out that the first one's 2. So it's just either 1, 3 or 3, 1.
Okay, yeah, true.
Mm-hmm.
I think you take k divided by the mode of the other one, so the remainder that the previous k had in respect to, and the previous n
Right.
minus 1 factorial is the same.
So you would k mod the previous factorial, right? So n minus 1 factorial. And that's it. That is what I did?
Yes.
Yeah. You just, because now you're going to iterate, right? And you have to, change the indexing for the new set of values. And of course, at the end, you decrease n. And you keep going until n is 0, because then you're done. You don't have anything else to work with. There's only one combination. And that's how you do it. Just keep doing this process again and again until n is 0.
Wait, can you just keep going there until we get the answer for
Oh, okay. So
the first value was 2.
Okay, so we can just say we have a string, right? And you put 2 to the string, and then after that, we have 3 and 1, right? And we say that k is 2, all right? So now we want this one, so we want this one. Oh, maybe I should do something like this. Make it more simple. Okay, we want this one.
Yeah.
So the first one is 3, okay? So then we get the size, it's like we did before. Add 2 minus 1 factorial is 1. 1 factorial is 1. So n is 2. So it's 2 divided by 1. Right? And, well, actually, I messed something up. So we don't want this 2. We actually want to turn it into back to 0 indexing. Right? So you actually want 1. 1 divided 1. Because then you're going to get this one. And then it's 3, right? What's that 1 here? It's 3. So then all you have at the end is 1, which is exactly what we need because 1 is at the end. And so you just do it all. K, you need to turn k into 0. So it's 2, you have to turn 2 into 0. So just, I think it's 2 mod 1. Anything mod 1 is just 0. And you only have to work with 0 at the end, and that's it.
So you get the last one.
Yeah, and then the last one, and then you add 3, of course, and then you do the last one, and it's simple. And then you add the 1, and you're pretty much done. Okay. Okay. So what were the extra data structures we needed aside from n and k?
A set, and an array, and like a string to store the answer or wherever we want to store.
Yeah, because we want to print a string. So we would add the first one. The first one when we're iterating, we would take from here, right? And then we have to change the value of n to -1. And k, you have to modulo itself by the previous factorial.
But then if you were doing this in Java, you'll need to use a different data structure, right? Because you can't index into a set.
I'm pretty sure there's a way to do that.
You turn it into a list.
You have to turn it.
Did I do it?
You turn it into a list.
Okay, in Python, I turned it into a list to get the 0 index, which might have taken a little extra time. And okay, that was a little bit of a cheat on my part, to be frank. Apart from the cumulative product that I put by importing NumPy.
Yeah.
Yeah, I imported NumPy and I cheated. That's why I love Python. You can just import things and they do stuff for you. But in Java, you can do it in Java though. You can get the index of a hash.
Yeah, because it hashes the values, like it doesn't.
You can do whatever you want.
I'm sure there's a way. I'm not sure.
Can you not just do instead of a set an ordered list? A list of 1, 2, 3, 4, 5, 6, 7, and then just remove it. It's gonna be all n, but it's still gonna be better.
Yeah.
Okay.
It's gonna be n squared, but it's gonna be better than n factorial.
So yeah, so I guess it doesn't have to be a set. It could be a list. An ordered list where you just remove the position, right?
You could use a linked list and it will still be constant time. Yeah, you can do it that way. Like if you use a linked list, it will be constant time.
Constant time.
Because it doesn't.
But to remove, but to
remove an index.
but to find
you
it.
need to iterate through it to find.
Oh no, but using an array list to remove might actually be fast.
So what, double link?
No, like you just need one linked list because you already know the index that you're gonna remove. You don't have to search for it because the equation gives you the index, and based on the index you remove the value,
Yeah,
right?
yeah.
So in a linked list, when you remove a value, it's constant time.
Yeah, but how do you find that value not being all m?
No.
Oh, they don't see this part.
Like they remove
Yeah.
Never add
You have
something
put a
to
hash
the
map
set?
with the keys, with values.
Well, you do it at the beginning.
That depends on the.
That's at the
genre of
beginning.
permutation.
Yeah, you add 1 to n
Yeah, yeah.
to the set in order.
Yeah, I think similar to what you're talking about, if doubly linked list with a hash map, where the
You come up here
and
and
then the value
last.
is a node, right? And then at that node, you can remove it by looking at its previous and set its previous next equal.
Can you give us your insight?
That might still not work because then you have to like update the hash
Do you-
map every time.
Yeah, but that's easy. It's easy to delete from a hash map.
Do you want to show us how it's done?
No,
Do you want to show us how it's done?
No, like.
Come on.
N squared. It's N squared.
It's n squared. If the best way to do this is n squared.
In Java, I think so.
But in Python, to make it into a list.
You turn into a list. That's also N squared.
Okay, so you can either do this in n factorial or in n squared. I don't know.
You can't do it in factorial. Time limit exceeded.
I know, okay, but I'm saying to do that's a solution.
I feel like you can.
I'm
do
saying
it.
if Lico was okay with it and didn't whine.
Yo, the Java code is so long.
No, I think you can do it
Are
in
you-
any time. You just have to build your own custom data structure for removing the stuff,
Yeah.
which takes all like.
I mean, an array list has the index, and it's a list, so removing is constant.
But when you
If we
remove
did
it,
like a,
There is an
oh, I was gonna say if you remove it in a array list, like you're creating a void, so everything else has to shift. You know what I mean? Like if you remove it from one.
You mean I have to change the index of everything else?
Yeah, so that takes linear time for everything to shift.
Okay, never mind.
But what if you swap
and
it?
what if it's a hash map with the keys as indexes?
What if you
Yo,
the
that will
values
work if you swap it.
As the numbers.
what if you swap
Mm,
the index,
that's a good
right,
point.
with the last one,
Deleting
right?
the-
You swap
No,
it
you get rid of the
and
order.
then-
You
That
get
will
rid
work for the first situation, but not the second.
Yeah,
Could
you
be.
get rid of the order.
Oh.
You need to keep the order as well.
You know what
This is
will work?
not open,
But then again,
That will work in linear time. You just have to swap it.
do you want to come up here and
I'm not sure, Eric, I'm asking, I'm like,
Wait, Pauline, what did you say?
so instead of, we have a hash map or a dictionary that has the keys is the index in the set and the value is the number. And deleting a key in a hash map. dictionary.
Yeah, but then you have to update the value.
yeah, all the values in here because I want to make this math equation keep working.
Okay, okay, so that's
I think n squared is probably the best we can do. I mean, what is my percentage?
Yeah,
And I think you can do.
Pretty bad?
Like 14.
14? Yeah, I did that on the fly. You know.
You sure, bro? Because you submitted a good amount of times.
I know, okay, well, I needed time to
No, okay, you
perfect
submitted
it.
twice. No.
I didn't look at the discuss. I didn't look at discuss.
Over a 6-day period.
No, that was me right now.
I mean, that's just one way to do it. This is how I did it, right? And obviously, there were a little bit of problems with the implementation of this set because turning it into a list to get an index took time to do, so,
How do I have a list?
oh, now it's following me.
Oh, crap, really?
Yeah.
Do the high five thing. No, delete this. Do this. Okay, move. There.
Oh, it's doing it. It's doing it, bro.
Talk about the space.
Okay. What's the space complexity of this problem?
What? It's open.
Right. Because you need n numbers to store in the set and n
No.
O of n memory.
You can do it in constant.
Why?
Because n is only equal to 9. You just pre-compute it.
What?
No, you need n factorial. You need n minus 1 factorial.
Yeah, you need n minus 1 factorial. You need
Yeah,
the,
you can
you need this
pre-compute
list.
that. How's it going, bro?
Yeah,
but
yeah.
Where would you store?
Where will you store that? Where will you store that?
But that's a constant. For no matter what problem you're doing it, you just do it like in the class.
This one right here.
Yeah.
Oh,
Can
I
you
see
not?
what you're saying. I think you're
Oh.
saying like, compute it every single time.
No, no. So, like no matter what n or k they give you, you're always going to do at most. This factorial is only going to go up to 9. So you just compute it beforehand, like do it in the class itself. Do like self dot fact is equal to that, because it's only 9 numbers.
Because the range.
Yeah,
Wait, what?
because it's
I
a
don't-
small
I don't-
number.
I don't-
So are you saying, okay, wait, so hold on a minute.
But it's still n because it goes until 9.
Oh, I get it, because then you would, to get the next, to get n minus 1 factorial, all you need to do is divide the current factorial But listen,
Yeah,
by the previous, by n minus 1. No, or n, no. Divide this one by 3, which is n, and you get 2. Yes, and then you don't need to store it. He's right. You're right. You don't need this, guys. You don't need this.
What you're saying is different from what you're saying, though. Like, I don't think you're both saying the same thing.
Look,
No, I know what he's talking about.
no matter what n or k they give you, if you pre-compute that all the way up to 9, that list is not going to grow with your.
Why do I need to pre-compute all the way to 9
But
factorial?
once you
Because that's the
take-
maximum.
but
It's the
that's-
But why do I
maximum
need to?
amount.
But if it's 3, why do I need to go up to that amount?
Pre-compute until 3.
Yeah, exactly.
Dude, then it won't be constant time. Oh, it's constant space.
It's not, it's linear space.
Listen,
That-
listen.
as soon as you reach 9, then
Listen.
But the problem, it only goes up to 9. So we only have to handle that. So you can technically
Oh,
say.
if you're looking at it in that perspective, then
Yeah.
it's like constant,
Yeah.
even though you're using it.
Look,
If
To
that's
get-
how you- if
It's
that's
not
how you're
gonna
looking
grow.
at it,
What
it's
if the
constant.
problem went up to 100? Okay, but
But-
there you would have to compute it.
listen, Lazaro, listen. You pre-computed up to 3 factorial. Then divided by the current number n, 6 divided 3 is 2. That's 2 factorial, which is exactly what I'm trying to do.
Yeah, but that doesn't even matter because in your solution, you're still using the list.
Okay, I know. I mean, how am I supposed to keep track of the numbers that I've already used?
No,
I don't want
know,
those.
I'm saying, but you don't compute that list depending on what n is. Just straight up do it when n is equal to 9, and then you have from 0 to 9, or 1 to 9.
Okay. Are you saying that makes it constant
If you
memory?
look at it, yes, if you look at it in the terms of the problem, since n only goes up to 9, it is constant.
So you're saying that because it's going to be constantly 9 despite what n is.
Since you know that the max is going to be 9, you can just compute everything, yeah.
Okay, technically that it is, but like, I mean like, all right.
So without that constraint of the problem stopping at 9,
Yeah,
it
if,
becomes linear.
if n goes to like 250, you can't do this. You would have to compute it depending on what n is. And then at that point, your space complexity will grow
Okay.
relative to your inputs.
I know. Okay, but
Which
base.
is linear, exactly.
Okay, but see, when we take 2 out, we're left with 1 and 3, right? We need permutations on 1 and 3.
What you guys are thinking. Which one are you guys trying to optimize? The list which contains the values from 1 to n, or the fact that?
Well, this was a set originally.
Okay, is that the one you guys are trying to like
Yeah,
optimize?
I'm
Yeah.
just saying it, put it outside the class and do it straight up to 9 already.
And then that's it.
Yeah, that's it.
Just saying that
So
we
no
want to
matter
return
what
this.
n is, you will have it already. You don't have to do it before you learn it.
Okay, look.
Yeah, if you combine that with what he's doing with the fact, then you have constant time.
Constant time?
Memory.
My bad,
Oh, okay.
constant memory.
Yo.
Okay, so how do we keep track of the numbers we need to, like, I put 2 and 4, say, and I'm left with 1, 3, 5, and 6.
Okay.
Yeah. I need to sort of, that's why I have this. This is,
But can you not declare that set outside of the class as well? Like outside of the method?
But it doesn't make a difference if you declare it outside or inside.
No, but then no matter what n is, you don't have to do that pre-computation because you already have it set in itself.
but that's the thing, I'm going to removing things from it anyway.
Yeah, but yeah, that's removing though, that's not adding.
Okay. So,
No, I get what you're saying. I just don't see how it's different from like what you already.
it's going to be n squared no matter how you look at this.
No, I'm not talking, no, I know it's n squared time-wise. I'm talking space-wise.
What do you guys think? Can this be done in constant memory? It can't. You kind of need.
I think it's like if you look at it from like I always looking at it like you have like at most 9, then it can be done in fact.
Okay, yeah, I know, yeah. No, that's true. But then with that memory, you're constantly removing stuff from it. So
How
you,
is that really adding?
Deal with that.
Like,
well, I guess you are removing stuff. Okay, never mind.
I think we can do it in linear time.
Can we?
can't.
We can?
Did I feel like we can?
No, that
Solutions that are
dude,
zero
that
minutes.
solution that said that said O of n, they were doing fine.
Actually, I know
That
what
goes
the,
through the
no,
array.
this is actually in
But they
constant
probably
time.
have it in a
This is in
hash map,
constant
bro.
time.
They probably had what?
This is in constant time, actually.
They probably had it in a hash map, bro. You're saying it's O of n.
Look, n squared, O of n. Okay, let's see. Bro.
I want to see the O of n solution.
You do it and then
Wait.
you use a linked list.
Dude, look, they're doing.
Do the whole thing. You're always removing like the
I'm
first
gonna be right back.
you're just removing one side.
This is incorrect. Look, they're going while factorial does not equal to 1, right? But they're popping, and inside the pop parentheses, they give it an index. That's O of n.
That's-
You can
Yeah, exactly. So
you
this
can
is
go
n squared.
wrong. You can
No,
do it
you
in
can only do
Because
this
you
in n
shift all
squared.
the numbers you
Exactly, so
have.
it's O of n. Like that
So in
operation is O of n.
You don't.
Are
You
you
don't need
do
to
it inside a while loop?
You don't need to. You don't need to use
What?
it. You can do it and
Well, basically, yeah, you have to do
Because
3,
the
right?
only
And these are all the
index
permutations.
ever gonna change.
And they're
is
asking for
first
the
index,
fourth one.
And when you
Right?
search
So that's
for one,
2, 3,
like
1.
it's just the next one.
Right?
It could be the second
So
and third
basically,
one.
either you
No,
can
so
compute
wait,
all of them
wait,
and
how
return
would you do
the
the
fourth
second
one,
and the third one?
For example,
which would
in
take a
the-
lot
in the-
longer than what
in
we're
the
doing,
second, in the-
right? Which
when
is
n
having a
equals
set
two,
of all
you
the numbers that are
modify it, you're looking
permutated,
for
and
the
now it's
equal
new,
to three.
keeping track of the factorial
Yeah.
we're on right now.
She's right.
We don't know which
Basic
index
Cali.
we're gonna remove.
Yeah.
It could be.
Wait, the same thing as if you were removing the first index. Like, can you go over your algorithm again? Like,
Okay, but so this is the 2. We're removing this 2. But this 2 is 1. This is the second one.
yes, and then now 3 shifts to be position 1.
Yeah.
And then when you remove 3, it's also in position 1.
Yeah.
So are you always going to be removing the value at position 1, or not necessarily?
Not necessarily. In fact, this position 1 could stay the same the whole time, which is what happens here.
No, like what I mean, the position 1 as an index 1 in a zero-based array. Like, where the 2 is, you know, that's like 1, right? Index 1.
Which one?
Like in the set, where the 2 is index 1 or not?
Yeah.
Okay, so like, isn't that the, because like in this example, that's the only one that we kept removing. We removed the 2, right? And then the 3 came to the place of the 2, and then we also removed the
Yeah.
3. And they
Wait.
were both at index 1, right?
Yeah, yeah.
So is that like how it's always gonna be, or is that gonna change?
This is how it's always going to be. You know, you just,
So essentially, are you always like gonna remove the value at index 1?
oh, you mean of this? Of yeah.
That's bigger.
Yeah, you're always going to remove the first one. That's the point.
Wait, give me a second.
What's a run and see at the time?
Okay,
Yeah,
so
I
wait,
probably understand what I'm
let's see.
saying.
What's n squared?
You know how I,
Eighty-one, right?
you know how like you remove
factor out the k.
this value, right? The 2.
Yeah.
Right? And then this 3 became at the position of this 2 because you removed this one. So
Yeah,
the
yeah,
index
yeah.
of this became 1. So you also remove this one, and then you weren't left with anything. Then you remove this one. Let's say you had other numbers. Would that be like sort of the sequence that they would be removed, or would that be dependent on this formula?
You know, well, this formula, this is the factorial, right? Oh, and I guess at the end of this, where's the red one? Oh, by the way, I guess if we're gonna keep it like this, factorial has to equal factorial divided n, right? To get the next one, to get the smaller one. Does that make sense?
Let me do it here.
Yeah, do it there. I mean, we trying to understand what you're trying to do.
No, like what I'm saying is like, are we always gonna be removing the 1 and this 1 or not?
No, yeah, you're not.
Okay.
No, I mean,
Still, like removing something like this, it is a one.
It is what? No, it's like if you're gonna
Well-
remove from just the first index, it's gonna be low.
Bro, 5%.
You see what I'm saying? So like, if that wasn't the case, then it would be like,
Right.
if that's not the case, you're gonna remove
That's the way it works.
the first index. right?
Because I told you, this is like, exactly multiplying against the constant.
It's much bigger.
Let me do it for n equal to 4 and see what happens.
I'm gonna end the live stream.
Yeah, okay.
I'm gonna end the live
So
stream.
you really try.
All right, guys, we tried to optimize this a little bit, but well, we kind of did. This part right here, there's less memory, but we're gonna try to figure it out.
No, they're doing